Hi everyone, 9.1 Exploring Rational Functions. Here we are. Let's go over the basic rational function, which I'll call everyday Joe rational. Use the table of values to graph the function of y equals 1 over x. So here are my x values. The associated y values, I'll just fill those in. Okay. Remember x equals 0, y is undefined, and then some negative values. All right, graphing rational functions. Identify the non-permissible values, NPVs. Identify and draw the vertical and horizontal asymptotes using a dotted line. Plot points on either side of the NPVs and connect the points to generate the general shape of the graph. So our first thing we're going to do is use green. We have a horizontal asymptote at y equals 0. I have a vertical asymptote at x equals 0. And if you recall, okay, since x is in the denominator, x cannot equal 0. So that's where my vertical asymptote comes in. And then y cannot equal 0, horizontal asymptote, because what happens if y is 0? Then I got a condition where 0 equals 1, and that can't happen. Okay, so we have y equals 0. So I have two asymptotes, and let's sketch it in. So in red, 4.0 to 0.25, 2 and 0.5. 1 and 1, and then 0.5 and 2, and 0.25 and 4. So that's what it looks like on the positive end. And then on the negative end, oops, I have negative 0.25 and negative 4. 1, 2, 3, 4. Okay, and then negative 0.5 and negative 2. 1, 2. Negative 1, negative 1. Negative 2, 1. 2, negative 2, 1. And all the way over here at negative 4, negative 0.25. So when I draw this in, folks, that is my Joe rational graph. Okay, the base rational function, the basic one, y equals 1 over x, has the following characteristics: non-permissible values at x equals 0. And we saw that from our discussion up here. We cannot have a denominator of equal to 0. Behavior near NPV. So as x approaches 0, the absolute value of y approaches infinity. Okay, so as x approaches 0, this way, look what happens to my y values. It approaches positive infinity. Okay, that's n behavior. Oh, sorry, that's behavior near NPV. And then n behavior, as the absolute value of x approaches infinity, y approaches 0. So as x approaches infinity, the absolute value of x, so let's just do the positive side. As x goes this way, what happens to y? Y approaches 0, gets closer and closer to 0. So that is our n behavior. Domain, it is x such that, well, the easiest way to do is just one value it does not equal. X does not equal 0. X is an element of all real numbers. Range, same thing. The easiest way to say it is just one value is restricted. Y does not equal 0. Y is an element of all real numbers. Equation of vertical asymptote, well, we saw that's x equals 0. Equation of horizontal asymptote, y equals 0. Notes on asymptote. Review. An asymptote is a line that a curve approaches but does not touch at the extreme ends of the graph. So I'll highlight the asymptotes here, folks. Asymptote, asymptote. Okay, for rational functions can have vertical and horizontal asymptotes. For example, f of x equals 1 over x minus 2. As x gets closer to 2, the graph of f of x gets closer and closer to the line with equation x equals 2, but will never reach the line x equals 2. Because if x equals 2, what happens? f of 2 equals 1 over 2 minus 2 equals 1 over 0. So as x approaches 2, the graph has an infinite discontinuity at x equals 2, and this is called the vertical asymptote of the graph f of x. This occurs because 2 is a 0 of the denominator of the rational function, so we showed right here. As x approaches plus or minus infinity, as that is, x approaches plus or minus infinity, the graph of f of x gets closer and closer to the x-axis, which is y equals 0. The line y equals 0 is a horizontal asymptote of the graph f of x, but the horizontal asymptotes may not represent an infinite discontinuity. We'll see that later on when we get more complicated examples. Vertical and horizontal asymptotes are often represented on graphs with dashed lines, but these dashed lines do not form part of the graph. They are just the restrictions. Okay, let us look at the effect of the parameters a, h, and k on the function y equals a divided by x minus h plus k. So let's throw a couple of parameters in there. So the graphs of the functions y equals 1 over x, y equals 5 over x, and y equals negative 12 over x are shown to the right. So let me color code these so it's easier to see. That's y equals 1 over x. That is y equals 5 over x. And then in green, that is y equals negative 12 over x. Okay, describe the behavior of these functions as x approaches 0. So, as x approaches 0, the absolute value of y approaches infinity. So, when I take a look at this as x approaches 0, so x approaches 0 would be, x approaches 0 would be this way. So as x approaches 0, the absolute value of y approaches infinity. So for the red graph, as we go x is closer to 0, then the y value goes up and up. For the blue function, same deal. Okay, and then the green function, this part, as x goes closer to 0, the y value goes that way, but we said the absolute value of y, that will approach infinity. On this side, as x approaches 0, this way, same thing, absolute value of y approaches infinity. So that is our end behavior with the x. Okay, letter C. Describe what happens to the values of these functions as absolute value of x becomes larger and larger. So as the absolute value of x approaches infinity, well, what happens to the y value? Y value approaches 0. So as x goes this way, x goes to infinity, okay, what happens to the y value? Well, for the blue and red graph, it gets closer and closer to 0. So y approaches 0. Okay, that's good. Green graph, same thing. Okay, x approaches infinity this way, absolute value of x. So y also approaches 0. So y goes that way. Okay, so that works. All right, letter D. Compare the graphs for any real value a. Describe the relationship between the graphs of y equals 1 over x and y equals a over x. So let's take a look at that. So for y equals 1 over x versus, in blue, y equals 5 over x, what can we say? The a value equals 1 here, and the a value here equals 5. This is we know this from our transformations, a vertical stretch about the a value about the x-axis by a factor of 1 by a factor of 5. Okay, let us compare y equals 1 over x versus, in green, y equals negative 12 over x. This is a equals negative 12, and then for the original function, that's a equals 1. So again, we have our vertical stretch about the x-axis, okay? And then here we also, because a is less than 0, I have a reflection in the x-axis. And you see that with our green function, it is flipped across that, reflection in the y-axis, sorry. Oh no, that is correct, yes. Sorry about that. Reflection in the x-axis, that's the a value, right? So you see where the red and the blue used to be, it's flipped down into quadrant 4. Okay, there's that. Okay, number 2 says sketch the graph of the functions y equals 1 over x. So I'm going to do that in blue, and y equals 5 over x minus 3 plus 2, and I'll do that in red, folks. Okay, remember to use brackets, very important. On your calculator, remember to use brackets, otherwise it's going to graph something completely different. So the blue graph, that's our classic Joe rational, so it's going to look like this. All right, so I'll just put 3 points down here, and then it's going to hug right along that x equals 0 asymptote, and also the y equals 0 horizontal asymptote, and then the other side here, I'll graph 3 points. Okay, so that's, and then let me draw some asymptotes here. And some asymptotes here. Okay, that's for the blue graph. Let's draw the red graph. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4.5. 5, 4.5. 1, 2, 3, 4, 5. 1, 2, 3, 4.5. Okay, and then okay, right about there, and then okay, right about there, and then the asymptote for this guy, I'll do it in, let's do it in orange. The asymptote would be right here. Oops. Right there. And I'll draw on this other asymptote right here. Okay, so in red, it's going to look roughly like this. Okay, and then on the other side, when I graph this, something like this, all the way over here, and then this graph is really, really stretched out. Let's see, right there, and then 1, 2, 3, 1, 2, 1, 2, 3. So this guy, okay, there we go. All right, so in blue and then in red, and then let's answer some questions here. Compare the graphs. How do the numbers in the transform function equation affect the shape and position of its graph relative to the graph of the base function y equals 1 over x? So if we are thinking about this format here, a, x, or a, h, and k, all the same values we're used to from our function transformation. So a equals 5. Let's call it out. It's a vertical stretch about the x-axis by factor of 5. Okay, we know that. H equals 3. That is a horizontal translation, 3 units to the right, and k equals 2. That is a vertical translation, 2 units up. Okay, and before I forget, I'm going to label my vertical and horizontal asymptotes. This one, that is y equals 0, and this one is y equals 2. Alrighty. Alright. Predict what will happen if x approaches negative x, or what will happen if x is, this is replacement notation, if x is replaced with negative x. Check your prediction using your graphing calculator. Were you correct? Describe what happened to the graph. When x is replaced by negative x, this represents a reflection in the y-axis. Okay, so what is going on? Y equals f of x is y equals f of negative x, or with mapping notation, xy becomes negative xy. Okay, were you correct? So I checked this. I will show you a Desmos. The answer to this is yes. It is a reflection, so I am correct. But I'll show you with the Desmos. Okay, so what does this look like? So y equals 5 over x minus 3 plus 2. That becomes y equals 5 over negative x minus 3 plus 2. Okay, next one. Reflect and respond. Are the locations of the asymptotes of the function y equals 1 over x affected if a vertical stretch by a factor of a is applied to the function? The answer is no. Okay. Vertical stretch does not affect the asymptotes because vertical stretch does not change. Look what it does algebraically. It does not change the non-permissible values, which lead to your asymptotes. Okay, so if I go from y equals 1 over x to y equals 5 over x, it's still x equals 0 as my vertical asymptote, right? So it doesn't change it. The only way to change the vertical asymptote is with a horizontal translation. You need to move it left or right. Number 4, can you tell from so likewise with a horizontal asymptote, if you want to change the horizontal asymptote, you have to apply a vertical translation up down, right? So that horizontal asymptote moves up down with a change in the k value. Number 4, can you tell from the equation of the transformed rational function y equals a over x minus h plus k where its graph has a vertical asymptote or horizontal asymptote? Explain. Yes, I can. Yes, of course. H equals 3. Therefore, we saw it in the graph. Therefore, the vertical asymptote is at x equals 3. Okay, same deal when we did all these transformations of log functions, exponential functions. You got to track that vertical translation. Any of these functions that have asymptotes, they're directly affected by the h and k values. K equals 2. Therefore, the vertical asymptote is at y equals 2. Okay, so notice that the horizontal translation value, h equals 3, affects the vertical asymptote. And that makes sense because the vertical asymptote has x values, x equals 3. Notice that the vertical translation factor, or the vertical translation parameter, k, the vertical translation affects the horizontal asymptote because we're talking about y values, moves it up and down. So that should make sense. Okay. 4b, last part here. Describe how the values of a function change as x approaches a non-permissible value. So as x approaches 3, so our non-permissible value here is x equals 3 because I have my vertical asymptote. This is my, so x does not equal to 3 because my vertical asymptote is at x equals 3. So as x approaches 3, the absolute value of y approaches infinity. So let's take a look at our graph here. As x approaches 3, so right here. So here are my x values, folks. So as x approaches 3, so I'm going this way. This is 3 right here. What happens? As x approaches 3, so as x approaches 3, what happens to my y values? Y approaches infinity, right? So y approaches infinity up this way, right? You can see the red part of the graph. It keeps going up, and that's to infinity. Okay, and likewise, that's why I put that absolute value of y here. The same is true on the negative side. Put a negative y in there, it becomes positive y, and it still approaches infinity. All right? Okay, everyone, over at Desmos, we're comparing the graphs of y equals 1 over x and y equals 5 over x minus 3 plus 2. So here's our Joe rational. We graphed this on the previous page, and then because of our non-permissible values, I have vertical asymptote at x equals 0 right there, and then horizontal asymptote at y equals 0 right here. Okay, and then we threw in this thing with y equals 5 divided by x minus 3. Okay, so right now, if I make this 1, right, it matches exactly our graph. So what happens when we go a value equals 5? Well, that's a vertical stretch about the x-axis. So there's a equals 5. And then we said, here's the weird thing, the horizontal translation, the h value, that will affect our vertical asymptote. But think of it this way, vertical asymptotes are written in terms of x, and we know h values affect the placement of the x value on our function. So if I go to the right, it's going to shift to the right. If I go to the left, it's going to shift to the left. So when I go to the right, h equals 3, I'm going to set a horizontal asymptote at x equals 3, and that should make sense. When I go k equals 2, that should make sense because so k equals 2, weirdly enough, it's the vertical translation. So you can see it vertically translate up and down. Vertical translation affects the horizontal asymptote, but I like to think of it as the horizontal asymptote has y values, and that's a vertical component, the y values, the vertical axis. So if I go to k equals 2, that's going to shift my horizontal asymptote 2 units up, and there's y equals 2. Okay, and there's my two graphs there. Okay, what if the other part is, what if I replace x with negative x? So what if I do this? Let's see if I can do it right in here. Yeah, so see what happens if I go x with negative x, it's going to reflect it in the y-axis. So if I throw a negative 1 in here, x to negative x, and you see it just flips over completely to the other side. Okay,